Okay, so let's start. So good morning, everyone. Um, so there's a third lecture on operating on file systems, the last part of the operating system. So far, what we did, let's recap till the last lecture. So we ended last lecture with the relationship between the file system and the disk. The figure here shows a typical basically file system organization. Here we see three physical storages, devices, disk 1, disk 2, and disk 3. Now, disk 1 in this case is divided into two partitions with two separate operating systems. Each operating system has a bunch of files and the directory, that is the index to access those files. A partition B is again another file system, and partition C or another file system, the C file system, comprises of both disk 2 and disk 3. So each partition contains files in that partition and a directory structure which contains information about all the files. So essentially a file system, there might be multiple file system in the same disk. Um, can it, okay, is there a question? If not, can everyone please mute? Okay. So let's talk about, this is basically typical file system organization. So, and you see that there's this, aside from the files, that this directory structures is something that the operating system needs to create. So let's talk about the directory structure. So what is a directory? Directory is basically index for the files. However, this directory can also be viewed as a symbol table that translates file names into directory entries. Right? So if you give a file name, I'll find out in the directory. I'll search. I mean, the operating system will search using the index, that is the directory structure, and find out the actual file location on the disk. Right. So let us start that what kind of operations you really need when you are writing a directory structures in a file system as part of the operating system. So what are the functions that you need to implement? Essentially, these functionalities are crucial almost or and available in almost any file system that you see. The first functionality is search for a file. And the reason is that we need to be able to search a directory structure to find the entry for a particular file. And you generally use the find command on the directory structure to find a file in Linux, at least. Then new files needs to be created and added to the directory. So if you want to create just a file, so in Linux, the everything basically has to be like any file will be in as part of a directory. So you can create a file by using touch and that file name, or you can create a directory using mkdir or made directory, a special type of file with mkdir command. So what does this commands do? They basically create files and add those file entries to the directory structure. When a file is no longer needed, we need to remove it from the directory. So you have this deleting a file is rm-rf command. Aside from them, this is like when you have all the files in a directory and you're navigating through the directory, you want to list all the files in that directory. So for that, you have the list or ls command. Um, there are also renaming a file, what Shubham was asking last day. So for even renaming a file, you have a rename command which will change the directory structure only. You're not changing anything on the disk, as I was mentioning. And sometimes you need to actually um, do a copy of the whole file system. So that will be done using directory structure, because directory structure is the index of the file system. So you would know what to copy, like what exact data to copy, what exact attributes to copy via the file system. And for that, you need to traverse the whole file system. Traverse meaning you need to go to each and every directory of the file in the directory structure. And the command for that is rsync with the A, V, and Z flags. So this is one of the most useful commands that I know, rsync AVZ, and it's almost ubiquitously used in any full backup of a directory. So these are the operations that operating system needs to support essentially on any directory structure, where the directory structure is basically a symbol table that translates file names into directory entries, which are basically pointers to the data on disk. So any questions so far? Because otherwise, after this, we'll actually see that what are the techniques to create these directory structures. What type of algorithms are used, and what type of things or techniques do we need for creating and enabling these operations. Okay. So now that we have seen what the operations are, these are needed for standard functionality of directories. Uh, Essentially, let's actually see that what when you're in circular. Oh, oh, I didn't know this. Sahil, can you unmute yourself and please let me know?
Sir, there was a circular that stated the institute would be closed because of election today, and hence less students have joined today. So,
Oh, I see. Okay, if that is the case, and tomorrow is also a holiday, it will be hard to make up, because we are losing two classes, and we are still only, I would say, 30% through the file system. So I am going to record this lecture. So record will be keeping, but if there is a circular stating that the institute would be closed to it, I haven't seen the circular. But if there is a circular should be closed today, then please feel free to leave. I'm not going to force any of you, but essentially I'm just going to record this and upload it in yeah, basically in MS Teams. So feel free to leave if you want to. This is just considered as an extra class, simply because we need to finish the file system interface and go for the implementation and quickly. We only have 1 week left. I'll give you it's 11:12, so I'll give you 2 or 3 minutes to, if you want to leave, and then I will again start from the directory organization. Thanks for telling me. Okay. Um, so let's actually restart. I'll upload this to MS Teams, and we'll have a doubt clearing session anyways tomorrow. Not tomorrow. In the next class, whenever it is. So essentially, when you are creating, let's actually start from here. So we know now the what is the directory. The directory that you see and love in the GUI is just an index to the actual data on disk. And this is something, this directory, this index is something that your operating system has created. Now, as a user, that is absolutely fine with you. But when you are going to write the operating system, you need to create a directory structure which is useful. So what does usefulness means? What do you need to check when you need to when you're writing a directory structure? So the aims is to enhance uh, efficiency. There are three things that uh, uh, we put here: efficiency, naming, and grouping. So accessing a file within any directory should be quick, right? So essentially, in a directory structure, the searching needs to be quick. That is what the efficiency means. Also, each user should be able to function without care about what are the file system operations, what the other user is doing. So two users should have same name for different files. That is also desirable. And because you can have your assignment 1.pdf, Sahil can have it, and Siba can also have assignment 1.pdf for him in the same machine. That is desirable. And the same file might actually have even several different names, like for a shared file. Okay. For grouping, essentially means that this is a little bit advanced. So what it means is that a good directory structure that sometimes, I mean, at least Mac provides, I guess Windows 10 also provides these days, but they actually try to do logical grouping of files by properties. So if you try to actually bunch your files in using this, like, show my files grouped by kind or size or name. So in there, you would actually see that a directory structure should provide quick grouping of files by properties. For example, all of your C codes together, all games together, all PDF files together. So have you seen this grouping, like this logical grouping of files by different properties in your operating system? I have, and that is in general when I try to actually do like sort by name or kind or by size or this things essentially. So that is what the directory organization generally means, to enhance efficiency, naming, and grouping. Now, how do you do that? What is the directory structure that will that we should use towards these goals? So the simplest directory structure is the single level directory. All files are contained in the same directory, which is easy to support and understand as shown in the figure. Okay. Uh, so essentially it means that if you have this directories, like a single directory for all the users. So if there is a machine like the CSC server or CSC machine or the lab machine, where all of you can log in. So for all of you, there is only a single directory. And in directory, what will be there? So if there are, say, 1, 2, 3, 4, 5, 6, 7, 8, 9 files, there will be 9 directory entries. Like cat, bow, test, data, mail, cont, hex, records. These are all directory entries, indices to the files. However, this is problematic, right? Because it just doesn't work in real life. Like, since all the files are in the same directory, they must have unique names. Like, there cannot be two cat entries which are basically exactly the same name for these files. And essentially that means that there is a problem with naming, because now two users cannot have different files with the same name. You cannot, Sahil and Siba cannot have two different files with uh, the same name, assignment 1.pdf, right? And it so essentially it I mean, if you have a single level directory, it won't be possible for you to work on a department server on your assignment 1 because it has a file name assignment1.pdf. So essentially, you might actually ask, like, is it so hard for us to actually use different file names like assignment1 underscore shiva.pdf, assignment1 underscore sahil.pdf? Actually, sorry, actually, it is quite common for the operating system to put a limit on the file names, and it is not hard to imagine that when the users are using larger and larger file names, they tend to reuse at least some of the file names, and they cannot just do it. In the single level directory, there is also grouping problem because it doesn't really, these files do not really give you any logical grouping. It's like all files are in the same directory. It's not PDF files in one directory and MP3 files in the other directory. So essentially, single level directory does not work in real life. So the standard solution to all this naming and grouping problem of a single level directory is to create a separate directory for each user. In this two level, so this is what we're showing is in this slide. So essentially in this two level directory structure, each user, so there is a master file directory which has directories for each user. User 1, user 2, user 3, user 4 has 4 directories, 4 symbol tables or 4 pointer tables. And each of them will point to its own user file directory. So this master file directories, they are basically pointers to other directory structure, which is the user file directory. This is called MFD, and this master file directory or MFD, and this is called user file directory or UFD. With so essentially with lists, I mean, each of this user file directory has the list of files for one single user. So when a process starts or a user logs in, first the MFD is searched by the user who is initiating the process or who logged in. Say this is user 2. And from that, the process goes to, when the user asks for a file, it goes to the UFD of that particular user, the user file directory of the user, and search for files. This MFD is indexed by user name or account number, and and each entry points to the UFD for the user. Essentially, this is absolutely common. And whenever, say, you log into your, or a student logs into a shared machine, or you log into your machine, you see that you have a home directory, right? Or something called desktop or even the username in Windows, or your home directory like slash username slash home in Linux. So this is essentially this two-level directory. Whenever you create a user in Linux, a home directory will be created. So this name two-level directory comes from this names from these two levels, right? There is an MFD, and for each user in the MFD there is a UFD. Now these user directories themselves must be created and deleted as necessary. And whenever you create, I mean, whenever the system administrator creates an user, a special system program is run which creates this UFDs, like user directories, and this entry is added to the MFD. There's the home directory of the whole system. Now this structure effectively isolates one user from the another, and these files should be accessed by, and in this way, these files, each of these files should be accessed by a path name like user1 go and then this. This is the path name that you should use, or in this two-level directory structures, you need the full path name for accessing a file, not only the name of this particular file. In this way, what is the advantage? You can have the same file name for different user. For example, here user 1 has a file called A and user 2 has a file called A. But because we are using the path names means user 1 and then A to access this data here. That means that user 2 can use the user 2 and A to access this data here, which are different data, but which has the same file names A, but different path names, user 1 and A and user 2 and A. So essentially, to actually find a particular file uniquely in this directory, two-level directory structure, we must give both the usernames and the file name for two lookups. However, still we don't have any grouping capability here, right? Because it is still like only two-level directory structure, and the UFDs doesn't really have say what you are more comfortable with, perhaps having a folder for your assignment 1, having a folder for your assignment 2, having another for assignment 3, and not put all the files in one single directory. That is not possible even now. And because you're doing two lookups, the searching time also increased a little bit. However, if you look into it, this two-level directory in it in slightly different way, that actually gives an interesting idea. You can think of this two-level directory is as a tree where oh, perfect, yes. So Shiva is asking, yep. No, you cannot have the same username. So remember that when that is actually interesting. So when you give your system administrator a name to create an account for you in a Linux machine, for example, they want to have a unique name. So also in MFD, you cannot have the same username. So at least the usernames has to be different again. Because there has to be, like here we're using the username, yeah, as a unique identifier, and you need to understand that the whole idea is that at least at some level you have unique identifiers for the users. So the way that we actually view these two-level directories, this is the tree of height 2, where we start the root directory is the master file directory entries, and the leaf is actual data. Right. So, or the leaves are in lieu of the actual data, you basically add here. So root and then cat. Now, if you view this two-level directory as a tree, no one is stopping you to actually have a tree of bigger, larger heights. That's the logical conclusion, right? What it means is that that natural way to improve the directory structure to a tree of arbitrary height. So this example is shown in figure, right? So essentially, it's like you start with the root where say there are three directories like spell, bean, and programs, and for each one of them, you have further subdirectories, meaning that this spell points to this directory structure, which is like stat, mail, and dist, and these two are directly in these two indices, stat and dist are directly pointing to portions in the disk itself. But mail is again a subdirectory which will point to another index. Out of that index, exp is a file, and others are again a folder. Sorry. So this tree is the most common directory structure. So each leaf node here, say this obj object, for example, it has a unique path name, which is this file name. So essentially, there is a root directory. Root has spell, bin, and so remember that even in Linux, right, you will see everything starts from root or everything starts from a user directory, and then you have subdirectories and subdirectories inside. So this tree structure directory is the way to implement, at least, you don't generally implement a single level directory or two-level directory. You generally tend to have a tree structured directory. And essentially each leaf node has a unique path with it. So what is the constraint that you still have? Essentially, in the same directory, you cannot have files with exact same names. I guess you already know that in a same directory, you cannot have a file like with like two files with the exact same names, right? So essentially, in tree structures directory, you use this path name. That is a full from root to leaf. This path name is the file name or unique identifier for the file. Now, um, essentially in the tree structured directory, you do you can have the efficient searchings because you are not really doing a linear search, but you are basically finding like you're going one level after other. You start from root and then you search within the next level. You then go for the, so essentially that would actually give rise to this because you are specifying the whole path. It gives rise to efficient searching, and it also gives you grouping capability because now you can have subdirectories called assign in the you can have a directory called assignment, and then you can have subdirectories 1 2 3 4 5 6. Within one you can have the .pdf file and .c file. So essentially you can actually group files by this tree structure. And I know that this might seem obvious to you, but even in some firmwares, if you look into the firmwares of some, I don't know, some coffee machine, it also a smart coffee machine also have an operating system, very basic one, which is also called a firmware because it is on the embedded system itself. And it often doesn't really have this tree, or it used to not have this tree structure directory. So there is no grouping capability. So essentially all the system files, and if you're developer, all your files are together in one single directory. That was a bit painful. Nowadays, most of the things run a version of Linux. So it comes with all this tree structured and grouping capability. So grouping capability just means in this case is logical to group similar files together. Um, and you can actually check essentially here like in your Linux system, you can check the current directory or the working directory or basically the directory that you are in using command pwd present working directory. And the system also provides you a few other commands that you all or most of you should know, because the virtue of doing the assignment one, which is changing directory, you have the cd command, right? Essentially, you have to specify cd and the path name where you want to go. Of course, you cannot cd to a file. You can only cd to a directory or a subdirectory. What does it mean? It means that cd command only traverses the directory structure. It does not go to follow the pointer, the final pointer to the end, to the disk. Now, you specify a particular directory using a path name. So let's talk a little bit about the path name in tree structured directory. Okay, because path names are super interesting and important, and they actually save us a great deal of time in searching, and also they enable us to group directories or group files together by use of directories. Path names can be of two types, absolute and relative. An absolute path name begins at the root and follows a path down to the specified file, right? That is what we talked about here. Is a root, spell, mail, proc, obj file. That is here. It's a absolute file name. However, a relative, there is something called also a relative file name, because you don't always remember the whole file name. So how about the operating system also provides a relative file names which defines a path from the current directory, because the user using cd command, like change directory command, or they are already in some working directory, like somewhere within some directory, right? So why don't we specify the file names, the rest of the file names relative to that file name, right? Like for example, if the current directory is root, spell, and mail, then the relative file name of would be like a/b, means that within the current directory there is a directory called subdirectory called a, and within a there is a file called b, and that is where we want to put our data or we want to read. So essentially, in this using this path names, you can create a new directory. So mkdir basically you specify a path name, and if that path name does not exist, make dir will create that directory. Or you can create a new file using touch and then full path name. So all we are telling here is basically used in Linux. Or you can delete a file called like using rm, which is remove file. Now, essentially, deletion is a little bit messy business, okay? Because now you have a tree structured directory. So what happens to all the subtrees? Like, so if you are in a current working directory /root /bin, then you run an rm, and then the system needs to decide what happens to the subdirectories and all the files in the directory. Like if you want to do rm in a single level directory structure, then all the files will be deleted, meaning the pointers would be removed, which means the state will be freed, and the state means the disk space will be freed. But now we have a tree structured directory. So what happens to all the subdirectories and files, or more technically, because you're a computer scientist, what happens to the subtree below your current node where you are in the directory structure? For example, if you're in prog, mail/mail/prog, what happens to all the files and folders, all the subtrees below prog? So it is basically, you might actually think that, this is obvious, I'll just delete everything. But generally, deleting anything is something is taken quite seriously in real world, right? Because you can delete mistakenly, and operating system should stop you doing that. So the MS-DOS approach is that the OS will not delete a directory unless it's empty. Meaning, to delete a directory, to user or the delete program must first delete all the files in the directory and remove all the folders. Okay. So in the MS-DOS, the beginning versions 30 years back, you cannot even delete. You will say like, there are files in the directory, I cannot delete. Go remove the files one after another. Now there is a subdirectory in it. In fact, even today in Linux, if you do just an rm and the directory name, it basically removes the files and say like, I cannot remove directories. I have to do it recursively. The rm minus r that you put, it means recursively removing the subtree in the directory structure below the current tree or below the argument. So essentially, in Unix rm command, this rf option means when a request is made to delete a directory, all the directories, files, and subdirectories are also deleted. To remove the index structure, because removing a link or pointer to the disk means that you are removing, you're forgetting about the file, others can use that space. But for directory, you need to do bookkeeping, meaning you need to actually remove these pointers and make the indices consistent. My point is that you need to balance the tree and do some bookkeeping that we are not going to cover here, but essentially you need to remove that node. Okay, so for deletion, rm is not enough simply because it is tree structure now. So we need Rm minus Rf, meaning recursively delete the entire subtree which is below the argument. Any questions so far? Feel free to please write questions here. But so far we talked about single level directory, all users one single directory. And then we talked about two level directories, and this is your more common, this tree structured directory. Now, tree structured directory has additional problems. What is that? Tree structured directory has a problem with sharing. Like this tree structure won't let you share files with other users, but it's needed. You say consider a coding assignment where two teammates are doing together. The files associated with this assignment can be stored in a subdirectory, right? And separating, so essentially that means that two teammates cannot share, cannot work on the same files in these things, like in this tree structure. So you want to work on the same file along with your teammate. How is it possible? So in tree directory, it is just not possible because you have this unique path for unique file and each user can access only their files. If you say that, give access to me to that file, what does it mean? Meaning that like in a tree structure, it only means that, you have to pose, like if I say like, give me access to Shiba's file, what does it mean? It means that in a tree structure, I have to pose as Shiba. Give me his credentials. That is the only way. However, people came up with slightly more involved and easier methods to do that. Essentially, they use something like an acyclic graph. That is a graph with no cycles, which allows directories to share subdirectories and files. So this is again an improvement over the tree structure. So the same file or subdirectory may be in two different directories. That's great. This acyclic graph is a natural generalization of the tree structured directory, right? In this case, like what is shown here, the file said dict and count. Okay. This is the index dict and count, and the pointer to dict and count also points to the same disk space that is pointed out by spell and words. So dict essentially, those who you don't know, dict is a Linux command which basically shows you a dictionary, and dict count essentially means the number of words in the dictionary. And then again, spell is a command to actually check for misspellings. And so what does it mean? So spell and words, the words that you check again misspellings, like whether a text file has any misspellings. So dict count and spell words, the words used in checking for spelling, and the word and the words in the dictionary would be exactly the same. That means they're shared together. Dict count and spell words point to the exactly same file space, exactly same file. So in an acyclic graph structure, note that a directory can have more than one parent directory. Now, what is a shared file? Okay. Now, a shared file or directory is not the same as two copies of the file. You're basically pointing to the same space. So with a shared space, only one actual file exists. So this is this thing here, this round symbol here. This is the actual disk space which is shared. So any changes made by one person, say you have the you change your assignment sales.pdf, that will also be reflected in your for your teammate. Sharing is so essentially any changes made by one person, like one process, is immediately visible to the other process. Sharing is particularly important for subdirectories because a new file created by one person will automatically appear in all the shared subdirectories. So essentially, The question is how to implement the shared directories, because now we want actually a mechanism where any changes by anyone made to the shared file who has access to it will be reflected by all the other members who are shared this file. Essentially, the technique that you see in your Google Drive or shared collab files. So how to implement it? One way to will be to duplicate the content every time. Meaning that there are actually, like, you can simulate acyclic graph directories using tree directories by using an extra process which will know that dict count and spell words are shared, meaning that any changes in dict count or spell words, like this files, if there are separate files for dict count, there is a separate file, spell words, there is a separate file. If that is the case, then some program needs to make sure both of them have the exact same data. This is actually a huge problem, and more so in a distributed system, because these directories, as you have seen, that these directories, these file systems can span across two devices, or it might even across two devices which are in two different continents. These are something called like they are basically talking, or they are basically connecting over networks. My point is that for a shared directory, if you have two copies which are always the same, this keeping always the same is called a consistency problem. This is a hard problem to solve. And really, we don't need that. For sharing, a better way for sharing is to create a new directory entry called a link. This is provided even in your Linux. Okay. So link is effectively a pointer to another file or directory. For example, a link may be implemented as an absolute or relative path name, and when a reference to a file is made, we search the directory. If the directory entry is marked as a link, then the name of the real file is included in the link information. So essentially, the link is another pointer to an existing file. So if there is a dict count and this file exists, spell words won't really point to this file space, but rather it will point to this absolute path name dict and count. So it will point to this. So if the directory entry is marked as a link, then the name of the real file is like the full path name is included in the link information. And we resolve that link by using the path name to locate the real file. So spell words only contain the path name. In fact, the Unix command ln-s can create these links, and a user can also remove links by calling unlink. So essentially what it means is that the directory entry here, the spell words directory entry is only a pointer, or is basically a full path name. It's not even a pointer. It's nothing but a full path name. So when a directory like your operating file system looks at a special file called this link file, it checks the file name we included in the link file and then access that file. So instead of a pointer, you put a file name. This is a simple and very elegant solution, because everything else remains exactly the same. Now, acyclic graph directories is definitely better than simple graph directories, but it is also more complicated. So, by the field, any questions so far in the acyclic graph directories from tree directories? So, acyclic graph essentially means that you basically have a linking, and via that you can share files. So essentially, this acyclic graph directory have several problems. For example, a problem is that a file may have now multiple absolute file names, right? And consequently, different file names may refer to the same file, which is like aliasing problem for programming languages. What does aliasing problem means? Essentially, it means that a same memory structure is identified by multiple variables shared over multiple processes. What does it mean? Meaning that changing one variable would actually change the memory and change the memory for all the other variables, which is basically a side effect. Because there are, so what is called aliasing? Because alias means fake names or multiple names of the same person. In this case, it means that multiple names of the same memory or multiple names for the exact same disk space. And if you use one name to modify the disk space or the data, this data got modified for all the other file names, basically the file paths. So deletion and all then this is the one problem. And then in acyclic graph directory, deletion might cause dangling pointer. Like for example, say if dict deletes count here, so dict is, say, assume that this is a user, it deletes the count. So what happens to this absolute name spell and words? So there has to be a way to like to bookkeep. Bookkeeping essentially means to keep track of what is going on in terms of deletion and whether all the links are actually pointing to, or all the links in the directory structure are actually pointing to the right data. So essentially the question is that when can the space allocated to a shared file be reallocated and reused? Otherwise, the directory entries would be invalid with no fault of their own. They didn't even delete it, but some other users delete the shared file, and now you cannot access it using the old file name. So essentially, in practice, Linux systems sharing is implemented by symbolic links, and the deletion of a link does not affect the original file. Only the link is removed. Recall what is the link? It's basically a path name of the shared file. That's it. It's a special file type which contains the file name, the full path name of another file. So if you delete the link file, nothing changes. So, however, for efficiency, we need to know which links are pointed to a file, because we need to know that who all are like who has shared a particular file. So we need to keep back pointers from each file to know which are pointing to them. So essentially, this is the first approach, like keep back pointer of links for each file so that I know that which links are deleted. So that this is for bookkeeping, to know who is pointing to a particular file. Another approach is just to leave the symbolic link on pointer to a file as it is and leave it on the user to find out. For example, if I delete a file, all the symbolic links will be invalid. But you are using a symbolic link to my file, so you won't know it. You will know it only when you are trying to access it. That also happens. How? So you sometimes, for example, you have ln minus s. That this happens mostly in systems programming. When you are setting up multiple like big web servers, for example, you do a lot of linking, like creating all these links to the system binaries. Now, if you uninstall a system, if I as root uninstall a system binary, the main file will go away. But oftentimes the links stay. So when you try to run a particular code, you will find you will get the error message that the binary could not be found, or we could not find the executable. And finally, another method to deal with this problem of sharing, basically managing when files got deleted or links got deleted, is to preserve the file until all reference to it are deleted. Right? Essentially means that you can only delete a file only when there is no links or no pointers pointing to it. And to implement this approach, some operating systems have a count of the number of references to a file. When the number is 0, it's safe to delete that file. So in acyclic graph, deletion means that the idea is that in acyclic graph, deletion means that you are not only deleting one file for one user, but you are basically impacting multiple users. So there are three options for handling that. One is that you want to know, like, keep back pointers of links for each file. Like, who else is this data shared with, so that you can tell the user that this is shared with X, Y, and Z. Do you want to delete it? The second approach is that leaving the link, like, you actually delete it and leave the and basically hope that other users are figuring it out when they try to execute. The file doesn't exist at all. And the third one is keeping a reference count of each file. It's like keeping back. It's not really back pointers, like fully back pointers. You don't want to tell the owner of a file that this file is shared with X, Y, and Z, and don't delete it. But you want to only say that this file is shared. And you can only make a user enable a user to delete a file when this file is, that number of references is 0. The difference between 1 and 3 is that for 1 you actually put the back pointers, for 2 you just have a count, no back pointers necessary. But the count needs to be handled, or counts need to be increased or decreased by the operating system. So the primary advantage of an acyclic graph is the relative simplicity of the algorithms to traverse the graph and to determine when there are no more references to a file. And we want to avoid traversing sheer section of an acyclic graph twice, mainly for performance reasons. For example, it is so essentially, if we improve, or basically if we extend this acyclic graph structure that we talked about so far into general graph directories, right, with cycles, sometimes it might actually create problems. And this is the most general way you can actually you can have your directory structure. So in a general graph, cycles exist. For example, here book is pointing to AVI, AVI is pointing to book, right? And that creates problems, or even larger cycles exist, essentially. Like here you have hype to, actually this is not a cycle. Actually book and AVI is the only cycle I can see here. So essentially, what are the problem with cycles? Because in the acyclic structure, you basically are constraining. You are in acyclic graph structure, you are constraining constraining the sharing of files by not having cycles. Like here, for example, one subdirectory has, like this book subdirectory has a API, book directory has AVI subdirectory, and apparently AVI is again linked to book. Now that is particularly possible. Okay. So essentially, the problem of cycles is that, remember that while deleting sharing directories, operating systems sometimes look into the reference counts. In a general cycle, when cycles exist, a general graph directory structure, when cycles exist, the reference count might not be 0, even if when it is no longer possible to refer to a directory or a file. The reason is the anomaly might be like is a possibility of a cycle in the directory structure. So essentially, book is pointing to AVI, AVI is pointing to book. Each one of them has a reference of 1. So even if you delete book for AVI, the reference won't really go away, because again, book is pointing to AVI. So to solve the problem of these cycles in general graph structure, graph directory structure, there are multiple approaches taken. One is to allow links to only files but not to subdirectories. This is the most common. So essentially, you cannot link to files. The book to AVI is not possible. You can do book to this mail. This is a file. You can link there, but you cannot link to subdirectories. Now that might actually have a serious usability problem, because now you cannot create a shortcut to your favorite movie directory. Another more elegant solution is basically garbage collection, which to determine when the last reference has been deleted and the disk space can be relocated. So garbage collection means that every time you delete something, you need to actually go through all these, like the whole directory structure, and making sure there is no dangling pointer, there is no cycle after the deletion. So essentially, garbage collection involves traversing the entire directory, marking everything that can be accessed, and then a second pass that collects everything that is not marked onto a list of free space. So you start with root, and then you basically do a BFS in the whole directory. You identify all the nodes that can be accessed, and the ones they exist in the file directory but cannot be accessed, you mark them as free space. Garbage collection is expensive, but this is also really needed multiple spaces. For example, I don't know whether any of you looked into ever had a file system error and you use some software to fix the file system error. What they do is oftentimes garbage collection. Do a BFS from the root node and find out the unreachable nodes and free them. But there is a reason that garbage collection is not doing automatically, but you need to initiate it as a user because it's expensive. Another solution is to start from an acyclic graph structure and check for cycles. And essentially checking cycle checking algorithm, you possibly already looked into algorithm courses, but this is expensive. You need to traverse the whole graph again to a BFS, and again need to check if you're encountering the same node twice. So it is as expensive as garbage collection. A simpler algorithm that people generally use is, or technique, is a special case of directories and links, is to bypass links during directory traversal. Because remember, this whole idea of this, like this book to AVI, AVI to book, these are basically links. These are shared directories. So we are not going to just traverse it. We will only traverse like when you're doing ls, or when you are doing a find, when you are doing an rsync, which requires traversing the whole directory structure. You will not follow any links, because there might be circular links. What is basically, means that in a book directory, there is a link which is pointing to the book directory itself. So during doing an ls or ls minus r, or when you are doing rsync, generally links are avoided to avoid cycles. So yep. So essentially, this is, I wanted to actually keep that picture while having this. So this is actually tells the graph the cycle detection problem in the graph. So essentially allowing only links and not subdirectories, garbage collection, and checking the cycles. But the point is that the simplest solution is bypassing links between directories traversal. So what you should remember, if you remember only a couple of points from this lecture, is that in a directory structure, you need shared folders. They are done using links, but they create cycles, and these cycles create problems. So everything that we do in the general graph directory structure where cycles are created by links is to actually avoid cycles during traversing, because that actually might give you infinite loop that might actually not be performance, that will not give good performance. Now, just a file, as a file must be opened before it's used, a file system must be mounted before it can be made available to process of the system. So so we almost covered the file concept of files, the actions that system calls that we want to read on files, and finally the different disk structure and directory structure. Disk structure essentially means same hard disk can have multiple file systems, same file system can span multiple directories, and directory structures essentially means you start from the single level, then you have this tree, two level, then you have this tree structure, then you have acyclic graph, and then you have the general graph structure. And in each of the cases, you are having more and more functionalities, but you're also having more and more problems. We'll stop here. And the last two parts are file mounting, how to mount the file system, and also a little bit about security on the file system before we can create the file system interface. So for these two, I would upload a small lecture in lieu of tomorrow's missed class. It will be really small, only a couple of slides, but I still want you to know what the file system mounting actually means and what does protection or security in the file system means. From the next week onwards, we'll start with if there is any doubt, we'll clear that from these two video lectures. And essentially, we'll start with the implementation of the file systems. So next week would be our last set of lectures on the implementation of file systems. Thank you so much for whoever stuck, and I'm ending this call. Please ask as usual your questions. So I am here, but ask your questions in doubt clearing session that we will have, and also in MS Teams. Thank you.